Hello, everybody. Good morning. Good morning. As usual, we'll give people a couple minutes to join us before we get started. Morning, Alyssa. Welcome. Morning, Maria. Good morning, Daisy. Okay, well, I think we can get started. So we're moving into our next section now, and it's actually two related things together. Hey, Monica. We're going to look at unit conversions, converting from one type of a unit to another, and then how to do that across domains like using density to convert between volume and mass, things like that. And then we're going to also apply that concept to chemical reactions and chemical equations and learn some things about how we calculate the quantities we need to do a chemical reaction. So first, we're going to start with some examples that don't sound very chemical at all. And this is just standard unit conversion stuff. And I should say before we go into this, if you've done this before, if you learned it in another class, and however you learned it works for you, just stick with that way of doing it. You don't have to do it the way that I'm going to talk about it today. But if you've struggled with it in the past, or you want to learn a different way to do it, or you just haven't ever done this before, this will be a good way to introduce that, to practice that. All right, so we're going to start with some statistics about this car, this 2018 Fiat 124 Spider. One of my colleagues put this together. I'm not sure if this is maybe her car. I don't know why she picked this one, but it's a good example. So these are all things that we've heard about cars before. This car can travel 26 miles per gallon of gasoline used, so you've heard that, fuel efficiency. It has an 11.9 gallon gas tank, and at a local gas station, gas costs 3.15 per gallon. Last as of last summer, it's a bit cheaper than that now, as no one's going anywhere. So first, we want to know what kinds of numbers are these, and how do we use them? So the first question asks, of the three statements above, circle the two statements that give ratios. So one of these is, and then the second one says, one of the statements gives a measured quantity. So one of these numbers is a measured quantity, and one of these is a ratio between two different quantities. And so maybe you can pick this out. The the measured quantity is the size of the gas tank, right? The gas tank contains 11.9 gallons. That's the size of it. It's a measured quantity. The other two quantities given here are ratios: 26 miles per gallon of gasoline and $3.15 per gallon. So let's think about those two ratios now and how we would write that as a fraction. So a ratio is a fraction. It's a relationship between two numbers, or it can be thought of that way. So if we want to know 26 miles per gallon, we might write that like in shorthand, like 26 mpg or something. But sometimes this is a difficult way to write it or causes some problems because it doesn't really express that ratio. So let's express that as a ratio. So as a ratio, we would write this as 26 miles per 1 gallon. So it's a ratio between the miles you can travel for a given size of or a given volume of fuel. 26 miles per gallon. And then it's really important when we write those ratios to always include our units so we know what we're talking about. So whenever we do all of these problems in this chapter and moving on, it's really important not to get rid of the units because the units are your key to actually going through and doing it correctly. All right, so there's our first ratio. And then our second ratio is $3.15 per gallon. So again, we're going to have our units. This time it's money, so the unit kind of goes in front, but it's $3.15 per 1 gallon. And so that's how we express a ratio. Whenever we see that per, we're talking about a ratio, and it needs to be expressed as a fraction like this. Okay, and then our measured quantity is 11.9 gallons. Notice that there are no other units here. Now we could potentially express that as a ratio by saying 11.9 gallons per 1 tank. We'll see if we need that or not. But at this point, it just makes sense to say that's a measured number, 11.9 gallons. All right. So then, how many miles can the car travel on a full tank? So what we want to do is multiply these numbers in a way that makes sense. And when we talk about the way that makes sense, what we are really saying is let's follow the units and make sure that our units make sense. And I see a mistake here. I'm not sure why I wrote that there, but this should be 11.9 gallons times our ratio here, 26 miles per each gallon. And that's going to give us the total amount there, which we can calculate. 11.9 times 26 gives me 309, and that is in miles. Now, there are rules for how you should round this number based on significant figures. We're not going to go into all of that in this class. We're just going to say, try to keep about the same number of significant figures as what you have in the problem. The actual rule is you always round down to whatever has the smallest number of significant figures when you multiply. But we're not going to be really strict about that in this class. So we'll say, okay, 309 or 310 miles total. So why doesn't the answer have gallons in the units? Well, one way we can think about that is if we look back at our equation here, we have gallons on top of a fraction here. We can think of that as being on the top of a fraction because it's just being multiplied. And so in that case, these would cancel each other out. So we're essentially dividing gallons by gallons and ending up with just miles. And that kind of thinking about the units is what can lead us through these types of problems. So that fraction we used here, this ratio, is called a conversion factor, and you can probably figure out why that is because we're moving from one unit to another. And in this case, we're moving in a totally different domain. We're going from miles, which is a measure of distance, to gallons, which is a measure of volume. So that isn't like a standard conversion factor. There's no official miles per gallon. It's going to depend on the car or on the vehicle. And so we get that number, and now we have a ratio, and we can do that conversion. So let's look at some different ways to write the conversion factor, and let's think about, are they all the same? Are they all the same ratio? Are they all the same ratio? So this is the one we kind of wrote before, 26 miles per gallon. This is going to be another way to write it because if it's 1 gallon, sometimes that can just be assumed there. I would still put the 1 there just to be really clear. We can also flip this over and say 1 gallon per 26 miles. Depending on what we're trying to calculate, it may be more useful to know how many gallons per mile than how many miles per gallon, but it's the same ratio. And so, in fact, these two are really equivalent. These are not exactly equal to these because they're flipped over. They give equivalent information for sure, but these are actually equal. There's 1/26th of a gallon per mile, because if you evaluate that expression, 1 divided by 26, we can think about it as a 26th of a gallon for each mile traveled. So these are just some little ways of manipulating the fractions. But depending on the question, we may want to use one or the other, and we're going to use the units to figure that out. So let's move now just into a more clear, or a way of just measuring distance. So we've seen these kinds of measurements before, inches and centimeters. We know there's 12 inches in a foot. We know there's 10 millimeters in a centimeter. We know there's 100 millimeters or 100 centimeters in a meter. But we haven't really talked about going between the two systems, the English or imperial units, which is inches and feet, and the metric units, which is centimeters. So 1 inch equals 2.54 centimeters. That's an exact number, so you can assume as many zeros after the 4 as you want. So if that's true, then you can finish this up. There's 2.54 centimeters in an inch. And here are some conversion factors. So can anybody look at these and tell me which of the 4, and we'll call them 1, 2, 3, and 4, which of these are incorrect ways of expressing that ratio? What do you think? 1, 2, 3, 4, or maybe they're all correct. But can you find any here that are incorrect ways of expressing this ratio between inches and centimeters? Okay, we got a few guesses there. I'll give you a hint. There are 2 that are wrong. Yes. Sounds right. Yes, you all got it. So first and third are wrong. Good job. Um, why? What's wrong about those? Yeah, they're flipped. And so one way that we can see this, because they look very similar. And so you can imagine how if you were doing this, if you were using these conversion problems in a on an exam or something, you can imagine how you could easily write the wrong thing and get it flipped. So how do we check that? How do we make sure we don't do that? Well, one thing is to think about the actual sizes. So think about how big a centimeter is versus how big an inch is. An inch is a little bigger, right? An inch is bigger. So anything, if we look at, let's say, the number 1 centimeter, 2.54 inches, think about how long that is. Those can't be equal, right? But 2.54 centimeters and an inch, that seems more equal. So if we think about the magnitude or the relative magnitude of these units, that can help prevent us from making those kinds of mistakes. Does it actually make sense that this should be equivalent to this? Remember that in these factors, the two should be, in this type of conversion, these two, the top and the bottom, should be equivalent. So if they don't seem equivalent, then you maybe have a problem there. All right. So which conversion would you use to change the length from centimeters to inches? So let's say we want to go from centimeters to inches. We have centimeters, we want to go 2 inches. We want to find inches. We're going to use number 4. And why? Because that's how we can get those units to cancel out in this way. So if we imagine that we have a number in centimeters, we want to multiply that by a factor that puts centimeters on the bottom and inches on top. That way, centimeters will cancel, and we'll be left with inches. So whatever the number is, making a plan with the units helps us to keep everything straight. So now let's do a real example here. How long is the American flag in inches? So you find a meter stick, and it's 152.40 centimeters. So we're going to start again by a unit plan. We are given centimeters, and we're asked for inches. So that means that our problem is going to involve starting with centimeters and ending up with inches, just like we did here. All right. So then we set up our unit plan. We start with centimeters. We multiply by something that gives us inches on the top and centimeters on the bottom. Then we put in our numbers. So we can add the numbers in whatever order we want, 152.40. And then we know that there is 1 inch in 2.54 centimeters. And so I think that answer is 60 inches. Yeah, thanks, Monica. So 100 and so because the 2.54 is on the bottom here, that means we're dividing instead of multiplying. So 152.4 divided by 2.54 gives us 60 inches. And that's how long that flag should be. All right, so here's another example that kind of takes you through how to do this for mass. You can take a look at that if you want. Let's go down to another example. Good question. So if it's on the exam, will you be given, or what do you have to memorize? So down a few pages in here, there is a table that tells you that. Here. So here are some things that you should know. We'll talk about the metric prefixes in a little bit. In addition, you should know inches, centimeters. You should know these. You should know there's 12 inches in a foot, 60 seconds in a minute, 60 minutes in an hour. Things beyond that, like pounds and kilograms, or quarts and liters, or gallons and liters, or something like that, those would always be given. All right, where were we? So over here. So here's kind of like a general idea of how to do this. Start with whatever they tell you, some number, some simple measured number, and start with that on the left. And then go to the right and say and put what you want as the answer, and then figure out how you can go from step to step to get the right units. So let's try one that takes a couple more steps. Convert 95 yards to centimeters. All right, so this one makes it very clear that this is the given number, 95 yards, and that's the answer. That's what we want. So we want to go from yards to centimeters. Now, maybe you know the conversion from yards to centimeters, and you can just plug that in, and that's it. But I don't know that. I don't know that number. What I do know is I know how many inches are in a yard, and I know how many centimeters are in an inch, because we just talked about that. So I'm going to make myself a little bit different path here using numbers that I know. I'm going to say, well, I know how to go from inches to centimeters. We just did that conversion. And I also know how to go from yards to inches. And I'm going to write those conversions here to remind myself too. I know that there are 2.54 centimeters in an inch. And I know that there are 36 inches in a yard. So then how do I set this up to do that with the actual numbers? Well, once again, I'm going to start with my units. So I'm starting with yards. And I want to turn yards into inches. And then I want to turn inches into centimeters. And that way, yards will cancel, inches will cancel, and my final number will be in centimeters. So now notice I didn't put any numbers here yet. I find, and again, you can do this whatever works for you, I find that sometimes the numbers confuse me. And sometimes I write the wrong number on top or on the bottom if I don't have the units there first. So if I put the units there, I can make sure that everything's canceling the way it's supposed to, and then add the numbers. So now I can add my numbers. I'm starting with 95 yards. I know that there are 36 inches in a yard, and I know that there are 2.54 centimeters in an inch. And now to evaluate this, I'm going to go 95 times 36 times 2.54, since all those larger numbers are on top. If there were other numbers on the bottom, I would then simply divide by whatever numbers were on the bottom. Since multiplication is, let's see, would that be commutative, but also associative, I guess. You can do it in whatever order you want. So I would go 95 times 36 times 2.54. And I get about 8,700 if we stick to two significant figures, 8,700 centimeters. All right, and then the final step, oh, you got a different number. Did I type something in wrong? 95 times 36 times 2.54. I think you typed yours in wrong. Um, can you do this differently? What do you mean? A different conversion. Yes, thanks, Monica. That's what I got. I suppose you could. I mean, if you knew how many centimeters are in a yard, you could use that number in one step. If you didn't know how many inches were in a yard, you could do feet and then inches. You could also not do it all kind of lumped together like this in one sequence. You could go step by step, and you could say, all right, I'm first going to convert the yards to inches, and then I'm going to convert the, yeah. So suggestion is to convert yards to meters to centimeters, and then divide by yards and meters. Yes, you could do that, but you would have to know how many meters are in a yard. You have to know the conversion between yards and meters. And I don't know that. So I use the conversions that I happen to know, which is I know how many inches are in a yard and I know how many centimeters are in an inch. If I could, yeah. So if you knew the conversion between yards and meters, then yeah, definitely do that. There's always lots of choices there. Yeah, so the actual calculator number that comes out is 8686.7. You can round that however you want, basically. Again, yeah, we'll do number 13. So you can do however you can round it how you want, basically, in this class. Again, the official correct way to do it is to round to the number of significant figures that the question gives you. But we're not going to be strict about that in this class. So you can leave the number with what your calculator gets. If you get a whole mess of decimal places, just, round it off somewhere that kind of makes sense. Okay, let's skip 12 because that's another kind of straightforward, but 13 is a little bit different. The speed of light is 299,792,458 meters per second. So that's again a ratio. What is the speed in kilometers per hour? So in this case, the reason that this one is different is rather than converting, starting with a measured quantity like yards and then converting it using ratios to inches and then centimeters, this question is actually starting with a ratio and converting it to another ratio. So meters per second to kilometers per hour. And that sounds kind of weird and different, but really what's going on here is we're kind of doing two conversions at the same time. We're converting meters to kilometers, and we're converting seconds to hours. So the way we set that up is very similar. Once again, I'm going to do it just with the units before we put any numbers in. So our first number is meters. Actually, it's a big number, so I got to leave a little more space than that. Our first number is meters divided by seconds, which is really going to be this big number of however many meters per 1 second. So then when I set up my factors, I want to turn meters into kilometers and seconds into hours. And it doesn't matter which order you do this in. So meters I want to cancel and instead give me kilometers. And then seconds I want to cancel and give me hours. But because seconds are on the bottom here at the beginning, I need to put them on the top in the conversion factor to get them to cancel accordingly. So seconds, whoops, not HN, that should be HR for hours. So let's look at how those units cancel. Remember that when you have a unit on the top and the bottom, it cancels out. So meters are going to cancel, leaving kilometers on top. and then seconds are going to cancel, leaving hours on the bottom. So you'll notice that our final quantity here is going to be kilometers on top and hours on the bottom. Okay, so let's fill in our numbers now. Here's our speed of light. There are 1,000 meters in a kilometer, and there are 60 seconds in an hour. So now to evaluate this, I can multiply through the top. So I'd go take this number and multiply it by 60 and put it here. And then I could put this number on the bottom, and I could leave it like that, but because kilometers per hour, we're really saying we want that number to be 1. So we really want to evaluate this. So we want to calculate this number times 60 divided by 1,000. So let's try that. I don't know if my calculator can handle that big of a number. Let's see. Okay, yeah, it can. It's just another really big number. So that would give me 17,987,547. I'm running out of room. Kilometers per hour. All right. So any questions about doing those? All right. Let's take a look at scientific notation for really big and really small numbers. You've certainly done this before. I can say that now. I never know if people know this or not. You may have forgotten it, but my fourth grader is doing this in his math class. So I assume if he's doing it in fourth grade that we've all done it at some point. But it might have been a long time ago for you. So we're going to review it. So when we look at scientific notation, we have something that looks like this. And it's a way of expressing big and small numbers in a more convenient way. But for us, the reason scientific notation is important, it's not just because it makes it easier to write bigger numbers, but also it makes it the precision more clear. So for example, you can we'll go through this table in a second, but let's say we measure something and it's 1,000 centimeters. So we make a measurement with a, I don't know, big thing, and it's 1,000 centimeters. We don't have a good sense of the precision of this number. Which of these digits are significant and which ones are not? Like which one, we talked about measurements with the certain digits and the uncertain digits. If you write a number like this, it's not really clear which number is which, because zeros can be significant, but they can also not be significant. So we don't know if this measurement means between 900 and 1100, or if it means between 1001 and 999. We don't know the level of precision. So if instead we write this as scientific notation, we can specify the precision that we're using. So if we write 1.000 times 10 to the third centimeters, which is the same number, just in scientific notation, now we're saying that all 4 of these digits are significant, and this number is between 999 centimeters and 1,001 centimeters. So it only varies by that last estimated digit. If instead we write 1.0 times 10 to the third centimeters, we're still talking about 1,000. Both of these numbers mean 1,000. But the level of precision is different. Now we're saying that this is somewhere between 900 and 1,100, because it goes back and forth, or it varies by plus or minus 1 on this last digit. Sorry, I didn't realize my head was in the way there. It varies by plus or minus 1 on this last digit. So how we write that, we're still expressing the same number, but when we use scientific notation, instead of just writing the number out like this, we're specifying a certain amount of precision. Okay, so also remember or recall that if those exponents are negative, Like in these examples here, we're talking about a number that is less than 1 and that we move the decimal place over to the left. So functionally to do this, if it's been a while since you did this, the way that we evaluate these is by the way most people I think about this is by looking at the exponent and using that to move the decimal place to the right or the left. So if we take this 7903 times 10 to the third, that means we're going to move the decimal place 1, 2, 3 places to the left, and that's 7,903. If it's a negative number, then, or I'm sorry, to the right. To the right, yes. If it's a negative number, then we're moving the decimal place to the left that number of spaces. So if it's -4, it's 1, 2, 3, 4. So that decimal place goes there, and that means we need 3 more zeros there in front of the 8. So this is 0.000831, which is right here. So if that's something you haven't thought about in a while, or that you're not real sure on, make sure you go through and fill out this table as some good practice on scientific notation. Because yeah, number 1 on the Mastering Chem with conversion and sig figs. Yes, we can look at that. Let me pull that up. So actually, before we do that, let's go on to just this next part, and then we'll do that one, because this may come into that as well. So one of the reasons that we are going to use a lot of scientific notation is because we have to use really big and really small numbers when we talk about different metric units. So like in this example, or well, in this table here are some of the metric prefixes and what they stand for in scientific notation. So my head is going to be in the way here, but hopefully you have this from Blackboard also you can look at. So for example, let's use one that we use a lot and that we know. Centimeters, centi, centigram, centi whatever, is given as 10 to the minus 2. So what does that mean? That means there are 10 to the minus 2, that a centimeter is 10 to the minus 2 meters, or 0.01 meters. So here's a little key on how to use that. The metric prefix and that whatever that base unit is, so 1 centigram would be 10 to the minus 2 grams without the prefix. So the prefix tells you where it is in here. The exponent always be 0. I'm not sure. Can you rephrase that? I'm not sure what you mean there. Okay, well, let me know. So will the number be the zeros it's missing? Not necessarily. It's not always. No, it's decimal places. So it's not always zeros. It's the decimal places. So for example, like in this first one here, you move the decimal place over 3 spots, but you're not adding any zeros. When you're moving to the left with a negative exponent, then you're going to have to add some zeros. But to the right, you may or may not add zeros depending on how many digits are specified. And we should also say you're always adding 1 less than the number of zeros if you're moving to the left. So this is 8.31 times 10 to the minus 4. If you move that decimal place 4 spots to the left, that's going to end up with 3 more zeros. All right, so back to the metric system here. This number 21 here, this is really the key. As long as you know which one is supposed to be bigger than the other one, you can come up with a conversion factor that makes sense. So if I said, if you're looking at a table like this, and you want to know, is a centigram bigger or smaller than a gram? Well, you should know, if you once you learn your prefixes, you should know that centigrams are smaller than grams. That's one of the smaller units. So that means that however many grams you have, it's going to be less than 1 because a centigram is smaller than a gram. Or conversely, there are going to be more centigrams in a gram. So the larger number is going to go with the number of centigrams in a gram. Let's also fix this. This should be micro, not miro. Yes. Yes, that's correct, Daisy. Yeah. Okay, so let's solve this and let's look at keeping the proper number of significant figures. So if we want to know how many meters, 2.5 meters is how many kilometers? Well, we know meters are smaller and kilometers are bigger, so we can set up our conversion in a couple different ways. We can go 2.5 meters, and then we can cancel meters and go to kilometers. Now, how we write this conversion doesn't matter. You can say there's 1,000 meters in a kilometer. You can do it that way. Or you can say that there are that is how this table is done. So you can say that's 10 to the third kilometers, which is how we would pull that from the table. So that number always goes with the base units. Either way, same idea. 2.5 divided by 1,000 is going to be 0.025. Whoop, sorry, one more zero. 0.0025. Let me move this up so you can see it there. And that is kilometers. We could also write that as 2.5 times 10 to the minus 3. Notice that's another reason that scientific notation can be handy. If we're just converting like in the metric system where everything is powers of 10, if we divide by 3, by 10 to the third, we can just add that as 10 to the third there. Do you need a 0 in front of the decimal? I mean, I guess technically you don't need it. I think it's a little clearer because just it makes it like because it won't get your decimal place is just a little tiny period and it could potentially get lost and stuff. It's not incorrect to not write that 0. I usually do just to make it a more obvious number, but no, it's not incorrect if you don't write the 0. No, it's not a significant. The 0 in front is not a significant figure. Zeros to the left of the numbers in a decimal like this are not significant. So this number, no matter how we write it, like this, like this, like this, that's still 2 significant figures, 2 significant figures, 2 significant figures. Let's do one more example actually while we're talking about significant figures, because these are measurements. So 2.50 millimeters is how many kilometers? Let's do that conversion. So 2.50 millimeters. And we can look at the chart and say, all right, we got 10 to the third millimeters in a meter, and then 10 to the third meters in a kilometer. So we could smash all those together at once, or we can do it in separate steps. Let's do it in separate steps just to make sure that we're clear here. So we're going to go from millimeters to meters, and then from meters to kilometers. Millimeters cancel, meters cancel, and we're left with, I'm just going to write it down here because I have a little more space, kilometers. So we can add those in here. We can say that there are 10 to the minus 3 meters in a millimeter, or we can say there are 1,000 millimeters in a meter, or 10 to the third millimeters in a meter. All of those should mean the same thing. And then we can say there are 10 to the third meters in a kilometer. Okay. So we're going to take millimeters and we're going to multiply by 10 to the minus 3 and then divide by 10 to the 3. Yeah, so we're going to get this really, really small number, which I think is more easily, in this case, written as scientific notation. So that's going to be 2.50 times 10 to the minus 6 kilometers. If we want to write that out as a decimal, we have to make sure to keep this 0 at the end so that we have 3 significant figures in this measurement. 1, 2, 3 significant figures. So in that way, if we keep it, yeah, I mean, you can leave it as a decimal as long as you make sure that you have the correct precision, so you have the correct number of significant figures. But as numbers get really big or really small, I would encourage you to become more comfortable with scientific notation, especially as we get into the moles stuff in the next section. On Thursday, we're just going to be dealing with really, really big and really, really small numbers, and you're going to be writing lots and lots of zeros if you can't do the scientific notation. So I would encourage you to get more comfortable with that, so that you don't feel like you have to always be converting between decimals, and you can just use the scientific notation. All right, so density is next, but let's do this mastering chemistry problem that was requested first. Second to log in here. Okay, so this was the first number 1 on the new assignment. Okay, I think I've got it here. This is the one about the aspirin. Okay, let me post it here for everybody. All right, so here's the problem. A low dose of aspirin is recommended. 70, and you may your number may be a little different because I think everybody gets a little bit different numbers on these. How many grams of acetylsalicylic acid, which is the active ingredient in aspirin, will a patient have taken over the course of 5 years if he or she takes 1 aspirin tablet daily? So, a lot of the problems, by the way, in the homework are this kind of like medical dosing type thing, because this is something that you may encounter. So, there's a couple different ways you can do this. We all kind of have this experience, so you can just sort of step through it as you would if this were your own common sense. You don't have to set this up in a particular way. But if we treat it as a conversion problem, we're given 78 milligrams per tablet and 5 years here. So the way I would think about this is I would say, okay, if I've got 5 years, I can convert. Well, here, let's do it this way. Remember, we think of our unit plan first. So we're going to go years to days. Um, to tablets, to milligrams, to grams. Now, this is probably overkill. Um, we probably don't need to take quite that many steps. But let's see how it goes. So in 6 years, and again, you can set this up as one big conversion, or we can do it step by step. Let's do it a little bit step by step, just so we know what we're doing. So let's go years to days. That's easy. 5 years times 365 days per year, or I guess in 5 years it's going to be we're gonna have to deal with a leap year, so we better add that quarter of a day per year. It's only two significant figures. It shouldn't really matter. So that's how many days I come up with here. And I know it's going to be one tablet per day. So let's get rid of this decimal point and let's just say that that is 1,826 tablets. So that's how many tablets I would take in the course of 5 years. Now each tablet is 78 milligrams, and then we can go milligrams to grams. So let's go 1,826 tablets, 78 milligrams per per each tablet. And then we want to go from milligrams to grams. So there are 1,000 milligrams in a gram. So I'll multiply 1826 by 78 and then divide by 1,000. And I get 140, whoops, 142.428, and that's grams. Now the question specifically says express your answer to two significant figures. So that means that I'm going to round this number down until I only have two significant figures, the 1 and the 4. So I can express that in two different ways, really. I'm not sure what exactly they're looking for. I imagine either one will be fine. So I can say that's 140 grams, because now that only has two significant figures. That 0 is not significant. But as we said earlier, it's not clear that that 0 isn't significant. I think it will accept this, but if we really want to make sure that we're saying there are only two significant figures in this measurement, then we want to express it as scientific notation, and we want to say 1.4 times 10 to the 2 grams, because then it is absolutely clear that there are only two significant figures in that answer. So you got it wrong 7 times. Was that like the calculation was wrong or just the rounding? Okay, so it did not accept 140. It only will accept the significant figures. Or you didn't try that. Oh, you read 144. Yeah. So if it says two significant figures, don't add more than that. I think it will give you the zeros. I don't think it will care about that. But yeah, don't round to extra ones if it's specifying that in particular. Okay, let's take a look at density. So density is something that you dealt with, or that half of you dealt with last week in your virtual lab, and the other half will do it this week. So here's a couple kind of questions to think about that. Which weighs more, a ton of bricks or a ton of feathers? It's kind of a trick question, right? A ton is a measure of weight, and so if they're both a ton, then they both weigh the same. But do they both take up the same amount of space? No. The ton of feathers you would expect will take up a whole lot more space, and that's because of the density. and that is the density, is the mass of a certain volume of something. So you can also say it's a measure of the space that a certain amount of mass takes up. So you can either way. Um, but generally, we express density as the mass of a particular volume, and it's usually a milliliter. When we talk about gases, we'll do density per liter, mass per liter, but generally we're talking about mass in volume per milliliter. Specifically, grams per milliliter is the most common unit for density. Now, that's a quantity, and that's a quantity that you should know. Particularly, you should know that water, the density of water, is about 1 gram per milliliter or a gram per cubic centimeter. A cubic centimeter equals a meter, or equals a milliliter. I say it's about 1 because density changes with temperature. So as temperature increases, the density goes down. It just a little bit. So if you're not using, let's say, I think it's about the third or fourth or maybe even fifth significant figure that it starts to become important to actually correct the density for temperature. Below that, you can just use 1 or 1.00 because the actual density is going to be 0.99 something something. All right. So when you use density as a quantity, there's nothing special or tricky about it. It's just another conversion factor. You can think of it as a ratio, just like miles per gallon or the other ones that we've done so far. This time, it's relating density, it's relating mass and volume, grams and milliliters, or grams and cubic centimeters. Some other things you should know about density. To calculate the density, we need to know how much space a given amount of mass takes up. So there's a couple ways to do that you will do in your virtual lab if you haven't already. If you have a very regular shape like a cube or something or a cylinder, you can measure the dimensions and then calculate the volume. You can look up the volume and the volume calculation equations, and you can calculate the volume. But that's often not super precise, and the reason is that you're limited by your measurement tools. So if you have an extremely carefully cut cube and you're using very, very precise calipers, then sure, you can get a good measurement. But a better way to do that is usually something called displacement. So take a look at this number 26 here. A piece of gold weighs that many grams and is placed into 41.1 milliliters of acetone in a graduated cylinder. The gold sinks to the bottom and raises the level of the acetone to 66.9 milliliters. So the mass of the gold here is given, and the volume of the gold we can get from recognizing that when that gold goes into the liquid, it's raising the level of the liquid, and it's going to raise it precisely by the volume of the solid, of the gold. So the difference in these two measurements, where the acetone was without the gold and then where the acetone is with the gold, gives us our volume. So 66.9 milliliters minus 41.1 milliliters is 25.8. And so that's the volume of the gold. And notice we don't know the shape of the gold or anything. We don't have to have some regular shape that we would if we tried to actually measure the dimensions of the length. We just plop the thing in the liquid, we look at the difference in volume of the liquid, and then we've got this our volume. So now to calculate the density, we just divide the mass by the volume. So grams divided by milliliters. And that gives us a volume in grams per milliliter or grams per cubic centimeter. So that's a very effective way of measuring density. Now you'll notice that the gold here is placed in acetone in a graduated cylinder. That may be because acetone is going to maybe have a flatter meniscus or something. But there's actually a problem here. I don't know if anybody's ever used acetone before. Can anybody think of a reason why acetone might not be a good liquid to measure volume in? Acetone is what's in like nail polish remover, for example. What might be a source of error if you're using acetone to measure volume in the lab? Yeah, exactly. It evaporates. Um, it evaporates fast, right? If you spill some acetone, it's just gone pretty quick. So you can feel it, if you get it on your skin, it like feels cool as it's evaporating, it cools off. So if you're trying to measure volume in acetone, that acetone's evaporating as you're measuring it, and you may not be getting a very precise volume measurement. So the right way to do that would be use a graduated cylinder that is stoppered, so that you can keep it from evaporating by corking it, and then quick put your gold in and cork it back up again, and then you should be okay. Using a really skinny graduated cylinder would help as well, because then there isn't as much surface area for the acetone to evaporate. Okay, so the last thing we'll do today is we'll use density as a conversion factor, and we'll do this one, number 27. What would the mass of 25 milliliters of milk be if the density of milk is 1.034 grams per milliliter? So just because we're using a density here doesn't change anything from what we've learned today. We're still going to treat this the same way. We're going to say milliliters of milk is what's given, and we want grams because it's asking for mass. Now, in this particular question, what unit it wants for mass isn't specified. It doesn't say give us the mass in kilograms. It doesn't say pounds. It doesn't say grams, whatever. So if it's not specified, I'm going to use the easiest one I can, which is grams, because that's just one conversion. So then we set this up as 25 milliliters of milk. Whoops, milk. Okay, there we go. Times a quantity that cancels milliliters and instead gives us grams, and that is the density. Notice I'm not saying multiply by the density or divide by the density. I think that's a dangerous way of trying to learn it, because depending on the problem, that density number may be on top and it may be on the bottom. If you just follow the units like with all the other conversions, then you'll know what to do. So we're always going to put that 1.034 next to the grams, because that is grams per 1 milliliter. And so then our solution is 25 times 1.034, 25.85 grams. And really, I would round that actually to 26, because we only have two significant figures here. So again, for me personally, it doesn't matter. You can do it however. If you're trying to be correct, or you're having trouble and Mastering Chemistry is telling you that you don't have the right number of significant figures, it's always you're multiplying by whichever number you're multiplying by that has the smallest number of significant figures, round to that. Okay, so on Thursday, we're going to extend this concept to chemical equations and talk about something called moles. If you want to work ahead a little bit on that and read those sections in the book, that might be helpful. And keep going with the Mastering Chemistry and lab, and that's about it. Other questions before we go? Yeah, thanks for joining. Thanks for participating. All right, well, I'll see half of you on Wednesday. Again, you can always send me questions on Discord or through email. And stay healthy and have a good couple days. And I'll see you on either tomorrow or Thursday. Bye.